So today we're going to do a continuation of the previous video. So the previous video proved a theorem which did not have this assumption of 1-to-1. Okay, so if you ignore the assumption of 1-to-1, then we proved already the following three items. Okay, so if you ignore 1-to-1 for a second, so if this is just any function from the set A to the set B, and E and F are subsets of A, then we have these three properties hold for the image of these sets under the function f. Now, if you are unclear about the notation here, the definitions, please refer to the previous video where we proved this theorem, okay? So in this case, we are adding the assumption that f is 1-to-1, and then with this added assumption, we gain full equality in the last two parts of the theorem, okay? So I've proved every direction of these set theoretic inequalities in the previous video, except for the following two directions, which are this set theoretic containment and this set theoretic containment. So this is all we need to show to complete the proof of this theorem, okay? So let's go ahead and do that. Okay, so let's prove this direction. And let me give myself a little bit more space. So we want that f of E intersect f contains f of E intersect f of f. Just make sure that this is correct. Yes. Okay. So the proof of this direction, we're going to let x belong to f of E intersect f of f. So then, and I'm going to try to show that x belongs to this set on the left here. That would conclude the proof. So this means that x belongs to f of E and x belongs to f of f. This is the definition of the intersection. Okay? All right, so this tells me that this tells me that by definition of being in the image set of E, this tells me that there exists an A in E with f of A equal to x. That's the definition of x being in the image set of E. And I know that there exists a different, potentially different A prime in F, such that f of A prime is equal to x. But now we notice that A and A prime have the same image under F. But since F is 1-to-1, we can conclude that A must be equal to A prime. Okay, so we know that f of A is equal to f of A prime, which is equal to x. So since f is 1-to-1, we conclude that A equals A prime. Okay? And A equals A prime then tells me that A is in E and A prime is in F. Well, A prime is equal to A, so A is in F. Okay? So we know that, let me just grab some more space here. Sorry, I'm trying to think about how to conserve space. Okay, maybe I'll just go on the edge of the board here. So A is in E and A is in F with, again, f of A equal to x. So this tells me that A is in E intersect F, because it's in both of the sets, with f of A equal to x. So therefore, by definition, X belongs to the image of E intersect F, which is precisely the direction of the set theoretic inequality that we needed to show. Okay? So I've taken an arbitrary element of this set, shown that it belongs to this set. Therefore, this set must contain the set on the right. Okay, so that works. Now let's move on to the next part, proof. So the next part is we want to show that f of E set minus f of f contains f of E set minus f when f is a subset of E. Okay? All right, and then again, for all the definitions of the set minus, you should really just watch the previous video. This is just a continuation of that video. Okay, so then to prove this set inclusion, we're going to let x belong to f of E set minus f. Okay, so this tells me that there exists an A in E set minus f with f of A equal to x. Okay, great. And so certainly this tells me that, well, A is in E set minus f, okay? So A in E set minus f tells me that A is in E and A is not in f, okay? So this tells me that that there exists an A within E. First and foremost, A is within E with f of A equal to x, okay? So we're almost there. So we A is in E minus f, so A certainly belongs to E, okay? And therefore, we're going to know, we know off the bat that, that x belongs to f of E. Now, the last step is just to show that x does not belong to f of f, okay? So okay, let's just look at the case if x belonged to f of f. If x belonged to f of f, then there exists an A prime in f with f of A prime equal to x. But this cannot happen because we know that f of A is equal to x, and A does not belong to f. Okay, so we would know that there exists an A in, so this A is in E. This A is in E set minus f. Okay, so A is in E set minus f tells me that A is not within f. So there exists an A not within f. Such that f of A is equal to x, and there exists an A prime within f such that f of A prime is equal to x, okay? This is a contradiction of the fact that f is 1 to 1. Since f is 1 to 1, it cannot map two different elements to the same image point x, okay? So A cannot equal A prime, okay? So A doesn't belong in f and A prime belongs to f tells me that these two pieces of information, A prime belonging to f, A not belonging to f, tells me that A cannot equal A prime, right? One belongs to the set f, one doesn't, so they're not equal. But f of A equals f of A prime. So this contradicts the one-to-one nature of f. So this is a contradiction. So what the contradiction does is it tells me that that this statement is false. So this statement cannot Okay? Right, so we started with assuming this statement, then derived a contradiction by the fact that f is 1 to 1. So therefore, I can add on to what I know here, which I know that x cannot belong to f of f. Okay, but now I claim we're done, because x belongs to f of e and x does not belong to f of f. So since x belongs to f of e and x does not belong to f of f, this tells me that x belongs to f of e set minus f of f. Okay, we're done.